Hello, everybody. Good afternoon, and welcome to this third installment of the series Classics in Molecular and Materials Modeling. This is a joint initiative organized by CECAM and MARVEL. I'm Ignacio, Pagonabarraga, the CECAM director, and we have here with us Nicola Marzari, the leader of MARVEL. And also, it's a pleasure to introduce you David Vanderbilt from Rutgers University and Raffaele Resta from Democritos, the speakers that we will have today. I would like to say that this is an initiative a bit unusual that came out we started to think about it in 2019 when CECAM celebrated its 50th anniversary. That was a good moment to look back and to reflect about what CECAM has brought fostering scientific cooperation in the area of especially of computational and molecular modeling, computational physics and chemistry. And obviously, the development of methods and algorithms has played a central role. And it was a good moment to try to identify how CECAM had contributed and had catalyzed or fostered the development of some of these seminal methods that have become classics and are used by the community. At that time then, in the discussions with Nicola, we really appreciated that he very rapidly engaged in and thought that this was really an interesting initiative. So we started it together from the beginning. And in this format, we identify seminal work on methods and identify the pioneers, the originators of these methods, and invite them to present them so that we can better appreciate what they have brought and also to understand what has been the impact, how they have developed and how they have been impacting our community. We do that by having presentations by the two speakers. So if I can move on and having now here. So coming to the layout of the session today, as I said, there will be a first talk by David Vanderbilt on conceptual aspects of the theory of electric polarization, and after a short break, a second one by Raffaele Resta on electropolarization, orbital magnetization, and other geometrical observables. But we also like to have a second part, or if you want a third part of this session, in which we want to create a more convivial or informal interviews where we can appreciate not only formally the concepts and the science behind the methods, but also try to approach or grasp what was the creative process, how these two people engaged and really got into these methods and ideas. And we think that also provides a complementary approach to understand how science evolved, how this is produced. And I think that's also very useful to the community. And I think especially for younger generations who normally don't have the chance to understand how this started. This is, I should also say, this is the first event that we hold online. I hope this will help to bring the previous ones have happened in the EPFL. And I hope that being online will contribute to bring more people to this special session. It's also a challenge for us, especially for this third part that is more informal, having to hold it remotely. Let's see how it works. So I hope all of you will enjoy this session. Before finishing, I also wanted to take advantage to indicate that there will be another classics installment before the summer, actually the 20th of May, and this will be about the methods to compute free energies of solids. And this was developed initially by Dan Frankel from Cambridge and Tony Ladd from now in Florida, and they will be our speakers. So if you like this format, I invite you also to note in your agendas this the next installment in the month of May. All these sessions, I mean, the previous two, and this one, and the forthcoming ones, are stored in both in the CECAM webpage and in the Materials Club webpage, where you can go and revisit them, or if you missed the previous two, you can also watch them. And also, I wanted to take advantage to mention that MARVEL, before summer, I mean, they also organize periodically distinguished lectures. And the next two ones in April and May will be delivered by Christine Persson from Lawrence Berkeley National Lab. She will be talking about data-driven materials, innovation and design. And in May, George Kresse from Vienna University will talk about ab initio accuracy for phase diagrams and the use of machine learned force fields. I hope you find this also interesting and want to join. And I will finish also by mentioning another online activity that we started this year in CECAM. We call the CECAM Mixed Gen series. This is a monthly event that is addressed to younger, researchers in the earlier stages. So we're thinking in PhDs and postdoctoral researchers who are suffering also from the pandemics. And the idea here is to have a more interactive event where we invite we identify a topic, an area, we invite an outstanding lecturer, and then there is an interactive poster session that is organized where, and then we select out of the posters 2 of them to be delivered also as lectures, and we invite more experienced researchers to be around so that they can interact with poster presenters. The next one will be this week on Thursday, and this will be a session on quantum Monte Carlo with the main lecture delivered by David separately from University of Illinois on simulating quantum systems. And in April, 8th of April, there will be the 4th on data-driven science, where the lecturer will be Claudia Draxel from Humboldt University, and she will be talking about from data to knowledge. So again, if you're interested, you can find the information, in this case, in the CECAM webpage for the distinguished lectures in the MARVEL webpage. And I hope you can follow up our coming online activities. And without any further delay, now I give the word to the chairman of today's event, which is Nicola. So please, Nicola, the floor is yours.
Thank you, Ignacio, and a very warm welcome to all of you. I'm counting 446 participants, so that's wonderful. And indeed, it's a crisis, but it's also an opportunity to, be able to do these activities online. So my name is Nicola Marzari. I'm here as the director of MARVEL at EPFL. And I think it's really a great personal and professional pleasure to welcome Professor David Vanderbilt and Professor Raffaele Resta today. Actually, both of them have had very close connections with EPFL. Raffaele has been a frequent visitor. Maybe we'll reminisce on some of this later on in the interview. And actually, I remember very well hearing David give a seminar in the Institute of Physics in 1992 on this, novel theories of polarization while he was visiting here, Irma and Roberto Carr. So with this, let me introduce the first speaker, David Vanderbilt. David holds a PhD in physics from MIT. He was a student of John Joannopoulos, and after that he moved to UC Berkeley as a Miller Fellow, and started in 1984 in Harvard as an assistant and then an associate professor. He moved to Rutgers University in 1991 as professor, full professor, and is there now the Board of Governors professor. He has been inducted in the National Academy of Sciences, in the National Academy of Arts and Sciences, is a fellow of the APS, a Simons Fellow, and also in 2006 a recipient of the Anizur Rahman Prize from the American Physical Society for Computational Physics. So with this, David, I welcome you very much. We'll have 40 minutes for your talk, 10 minutes of questions, and everyone is welcome to write their questions in the question and answer session or to raise their hand, and then I'll unmute them and so they can ask the question live. David, the floor is yours.
Okay, so let me put my slides up. I hope you see that.
All great.
It's a wonderful opportunity. I really appreciate. Oh, now I've got this. Hold on a second. Oh well, let's just. I've got my. Oh shucks. Sorry, I've got my screen. Let me stop my share for a second and restart. Okay, I'll live with this. Okay, the talk I plan to give today is on the theory of electrical polarization, and then also touching on orbital magnetization and anomalous Hall conductivity. This talk is different from almost every other talk I've given. I decided to focus on conceptual aspects, and you're going to hear almost nothing about actual the Berry phase theory and the formal development of it. I'm doing that in part because I'm putting some of that on Raffaele, I guess, to manage some of that in his talk. But also, I think it's kind of an underappreciated aspect of the theory. This part of the this talk in some ways resembles the first chapter of my book, which came out recently on the theory of Berry phases and so on. And in that first chapter of the book, I do something similar. I really focus on conceptual aspects without introducing mathematical descriptions yet, because the conceptual aspects do give us a huge number of hints about what the mathematical framework is going to have to look like. What I'm also not doing is giving a historical introduction. I'll do a little bit more of that during the discussion section that comes after Raffaele's talk. And so it's neither a straightforward introduction to the form of the theory, nor a historical discussion of how it came about, but perhaps a discussion of how it should have come about, how we should have understood from more elementary aspects of understanding the physics of classical and then quantum mechanical insulators, how a framework of this kind had to be developed. For example, the fact that polarization can't be a single number. It has to be a multi-valued or only well-defined modulo a quantum. And so to do that, I'm going to begin by introducing a kind of a classical theory of point charge systems first, and explain how these aspects have to appear there, and then basically say, well, why should we be able to do better when we do a quantum mechanical framework? The quantum mechanical framework has to have the same kind of behaviors. So most of the talk will be in the context of the theory of polarization, but then at the end, I'll talk some about orbital magnetization and anomalous Hall conductivity. Okay, so what's the problem with the theory of polarization? I think most of you are probably familiar with this. In the simple textbooks, you have this sort of Clausius-Massadi picture in which solids are composed of little polarized entities that are well separated from one another, and you calculate the dipole moment and divide by unit cell volume, and that's the polarization. So there's no issue. But once you go to a quantum mechanical view of a crystalline solid, you have integer point nuclear charges, and then you have distributed electron clouds due to quantum mechanics. And this is a sketch of sort of what the electron clouds might look like in a toy model. And there's no way to divide this into unit cells in a natural way. This is a picture that I love and was generated by our chairman, I don't know, more than 20 years ago. I hate to think how long ago, but it's a beautiful picture of charge density contours in lead titanate, illustrating that there are no well-separated charge entities, that the charge density fills the entire unit cell. And so there's no obvious way to divide it into simple dipole entities. So again, just to belabor the point a little bit more, I have this kind of crystalline solid. It has broken inversion symmetry, so it should have a polarization in the vertical direction. But depending upon where I put the unit cell, and then I compute the dipole moment per unit cell, and I'm going to try to attribute that to a polarization. Depending upon where I put the boundaries of the unit cell, here I've got a lot of negative charge at the bottom, so the polarization is up, and here the polarization is in the other direction. So the polarization depends upon where I choose my unit cell boundaries, which is clearly not acceptable. And the conclusion from thinking through this problem and a number of related problems is that even if you have an exact and precise knowledge of the bulk charge density everywhere in the unit cell in the bulk of an insulator, that's not enough, even in principle, to determine the polarization. The polarization has to come from some further information that's not simply available in the charge density. And the heart of the problem is that a dipole is basically a coordinate times a charge density, and this kind of operator is not, expectation of this is not periodic in the unit cell. It grows without bound as R becomes large, or another way of saying it is that matrix elements of the position operator are not well defined in the block representation. Okay, so what to do about this? Well, what I'd like to do is to imagine for a moment that the universe is built on a different physics. There is no quantum mechanics. It's purely classical. And all the charges are integer point charges, which are red here. Those are like nuclei. But also, instead of electrons, we have integer negative point charges. If you like, you can think of this as an extreme ionic picture where these are sodium and chlorine ions or something like that. But for the moment, let's just say that they're a fictitious physics of positive and negative point charges. And so we have crystals, and we want to be able to describe what is the polarization of this crystal. So, we introduce a unit cell and we calculate the dipole moment in the unit cell. In these slides, I'm using lowercase p as a polarization displacement vector, which just points from the negative charge to the positive charge. And then the conventional polarization is this displacement vector times the quantum of charge divided by cell volume, right? So that would define the polarization. But how did I get to choose that unit cell? I could have just as easily chosen some other unit cell. And in this case, the charge displacement vector is in the opposite direction. And so I have two different values of polarization that seem equally good. And they differ, of course, by the vector that points from one positive charge to another positive charge, which is nothing other than the lattice vector. So this says that the polarization is only well-defined modulo a quantum, and that quantum is the quantum of charge times the lattice vector divided by cell volume. Of course, there aren't only two possible values of polarization. I could choose a unit cell perversely to include, that negative charge and that positive charge, or that negative charge and that positive charge. So in fact, there's an entire lattice of polarization values, all of which are equally valid descriptions of the electric polarization in this solid. So that sounds very unsatisfactory. If you have many, many different values of polarization, which one is the right one? That, how are you going to ever calculate anything? Well, three. Okay, so what you can calculate, of course, is the change in polarization. And Raffaele is responsible, I think, in the early 90s for pushing the community in the direction of looking at changes in polarization. So here, I'm going to look at changes of polarization as I move the negative point charges from some initial position to some final position. And of course, in that case, the change in polarization, well, since it's a negative charge, I drew the arrow backwards, but the change in polarization is just related to the shift of those negative ions. And knowing the path along which this ion traversed, we have a unique value for the change in polarization. And that would, for example, describe how much charge is pumped from the left surface to the right surface of the sample. That could be something that's experimentally measurable. Of course, there are other ways for the charge to go from the initial position to the final position, and here's one of them. And of course, this reflects the fact that the polarization is multi-valued. And so in this case, the change of polarization was in the other direction. And the difference between the first change in polarization and the second change in polarization is, again, the polarization quantum. So the story here is that if you follow some continuous, I'll use the word adiabatic when I get to quantum mechanics, like adiabatic path of the system as it evolves from one state to another state, the change in polarization is well defined even up to everything if you know the path. If you don't know the path, it's only well defined up to a quantum. Another aspect of this, or another way to look at it, is to think in terms of closed paths. So if I look at all possible closed paths in which the ions undergo some deformation and then come back to their initial positions, then either the polarization change is 0, which is what I just showed, or it's also possible that I can find paths like this one, where it comes back to its initial configuration. In the bulk, there's no distinction between the initial configuration and the final one, so it really is a closed path. But of course, the result of that is that we pumped a charge by a lattice vector. And so the change in polarization on that path was just the quantum polarization. It's electron charge times the lattice vector by which the charges were displaced. So this is what the theory of electric polarization has to look like for systems of point quantized point charges in some fictitious physics. And here's a summary. Polarization is only defined up to a quantum. Changes in polarization are well defined if we know the path. The change in polarization is independent of the rate of traversal. For closed paths, the change in polarization is an integer times the quantum of polarization. This is called quantization of adiabatic charge transport. The polarization, I haven't really gone into this, but the polarization obeys desired relations. Here, I have two derivatives of the polarization, and as long as you're taking derivatives, you don't have to worry about this ill-determined quantum, because you're only making small changes, and you can follow the polarization that you're interested in. So one is the change of polarization with respect to time is a macroscopic current flow, and the gradient of polarization with respect to space is some excess bound charge. And related to that is that the surface polarization is given by the bulk polarization dotted into the surface normal. This is what a theory of polarization looks like for a system of point charges. What about for a truly quantum mechanical system? Well, why should we expect to be able to do any better? I mean, the whole community before 1992, 93, when this formal modern theory of polarization, so to speak, emerged, we were very used to calculating things as expectation values of some operators. Charge densities, total energies, forces were all expectation values of charge of operators. And that always gives you a single absolute answer. But any theory for electric polarization that gives you a single absolute answer that's supposed to say must be wrong. Must be wrong, because why should we expect our theory to do any better for a quantum mechanical system than it did for this even simpler system of elementary point charges? So we cannot expect the polarization to be described by any formula that writes it as an expectation value of an operator in the same way that we would for a charge density or a force or a total energy. So I don't think we appreciated this enough at the time. We were sort of forced into developing this theory because we were trying to calculate things in barium titanate, and we weren't really thinking deeply enough. But this, in retrospect, is, I think, how we should have approached the theory. And so a quantum theory of polarization has to have these same features. It should have all of the same features that the previous theory had. And in particular, it should obey the quantization of adiabatic charge transport. And I regard this as sort of the most crucial feature, because once you have this feature, then the other features more or less follow. And so let me try to explain that a little bit. So what do I have here? What I have here is a simple tight binding model with 3 sites per unit cell in 1 dimension. This is the x dimension. This is the site energy. And there are hoppings that I haven't drawn between neighboring sites. And the site energies alternate in some way on every 3rd site. And here I've put 2 of the site energies lower in energy. So if there's an electron in the system, it'll tend to sit in this lower energy site. Of course, the electron charge density is really distributed. If you want to, you can think of this black dot as the center of a Wannier function, which is somehow distributed but exponentially localized in the vicinity of this particular center. So that's what I wrote down here, Wannier charge center. And here's the lattice constant. And now suppose I make a slow adiabatic change of the Hamiltonian by changing some of these site energies. So for example, I lower one of the site energies and then raise one of the site energies. And now the system is shifted by 1/3 of a lattice constant. And then I do it again, and it's shifted by 2/3 of a lattice constant. And I do it again, and now it's shifted by a full lattice constant. And so now the Hamiltonian is exactly back in its initial Hamiltonian. The Hamiltonian has gone in a closed loop and come back to itself. But in the process, it looks like we've moved 1 electron of charge minus e by 1 lattice vector. And so the polarization is changed by that divided by 1 unit cell. Now, clearly, if this site energy difference were, very large, like 100 electron volts, then this electron would be very, very tightly localized to this site. And it would be true that when we move it by a lattice vector, we would have exactly this change in polarization. In the theory of quantized point positive and negative charges, we would also have exactly this value. But in the real quantum mechanics, in which the charge distribution is really distributed, it's described by Bloch electrons and so on, we would be forgiven for doubting that the exact change in polarization could possibly be the same exact value. We would expect that we would have some corrections from the fact that we have quantum mechanical charge clouds. Well, the fact is that if it's true that there are corrections, then we have serious problems for making a theory of electric polarization. So conversely, if it's the case that those cyclic changes in polarization around a closed cycle are always giving you 0 or the quantum of polarization, then we can develop a theory of polarization. Okay, so let me just explain that in the next 2 slides. So again, if I go around a closed loop, this is some parameter space that I'm drawing here, some curve C in parameter space, and the polarization change over that loop is given by, so I'm saying, suppose I have a proper theory of polarization. The polarization is a function of the instantaneous condition of the system described by parameter lambda, but lambda in turn varies slowly with t. And in quantum mechanics, we have to assume that the rate of change of lambda and therefore of the Hamiltonian is slow enough that we're in the adiabatic limit. That is to say that basically the inverse of the time scale on which the Hamiltonian is changing times h bar is small compared to typical energy spacings between bands or levels. Okay, so the change in polarization is given by integrating up the time rate of change with time. But if I use the chain rule, this is the change of polarization with respect to parameter, and then parameter with respect to time. You cancel the times, and it's really just a change of the polarization with respect to parameter times the parameter, right? So this is essentially Resta's famous formula from 1992. And so if this thing is always equal to an integer times the electron charge, that is to say, if it's always following the quantum, then we can develop a proper theory of polarization. The polarization is well-defined modulo an electron charge, even in quantum mechanics. And the reason for that is illustrated in this figure here. Here, the polarization change in going from lambda 1 to lambda 2 between two different configurations of a system, for example, some ferroelectric where the titanium atom is moving off center or something, is given by integrating up the change in polarization along path A. And if I do it along path B, I get this other value, and I ask whether those two values are the same or different. And they'd better be the same if we have a proper theory of polarization, or at least they'd better be the same up to a quantum. And they are the same up to a quantum if what I said on the previous slide is true, namely if the closed loop is a quantum. And the reason is very simple. The path that goes from lambda 1 to A is the same as the path that goes all the way around from lambda 1 and follows the closed path and then follows B back to lambda 2, right? So so that's what's written in this equation. And therefore, if this thing is quantized, it means that any two measurements of any two calculations of the change in polarization will agree up to a charge quantum. And of course, this is just like the physics that I described for fictitious physics of integer point charges. And also this integer n, I can say is quote unquote normally 0, which is a good thing. Most of the time we don't have to worry about it. And when we do have to worry about it is basically when there's some obstruction to shrinking this path to 0. So if I make a slight change of this path C, the integer value of this loop integral can't change smoothly. An integer value can only become ill-defined or jump. And so if there's a region here in which the system is no longer an insulator, but there's some gap closure, then it's possible for the loop integral to be a non-zero integer times the charge quantum. And so we do have the situation like this, where in principle, you could have two configurations and the change in polarization would depend upon path A or path B. But that only happens if, if there's an obstruction to collapsing the loop to a point, at which point, obviously, the loop integral has to be 0. Okay, so I said, if this quantization of the closed loop is correct, then we have a theory of polarization. Can I argue on physical grounds that this hypothesis is correct? That is to say that closed loop changes of polarization are always 0. And let me give two kind of heuristic justifications of physical arguments as to why that's the case. So the first of them has to do with this equation I wrote down on one previous slide, which is that the surface charge density is equal to the polarization times the surface normal. So, in the ordinary Clausius-Masati picture, that basically says that there's an electric polarization, and then I have some positive bound charge on one surface and a negative bound charge on the other surface. And so if we have a proper theory of polarization, we expect the same thing to be true, at least under some conditions. And the proper conditions to consider in this case are, first of all, the bulk has to be a periodic insulator with a gap. The surface also has to be insulating with a gap which is common to the gap of the surface, with a Fermi level in both gaps. And the surface has to be a perfect defect-free periodic surface. So with those caveats, then it should be the case that the surface charge density is given by the bulk polarization. And so we tend to think of surface charge density as a surface property, but under these conditions, it's not really a surface property. It's a symptom of the bulk polarization, except that the bulk polarization has this uncertainty modulo a quantum. So that means that the surface charge density would also have to be uncertain modulo a quantum. And actually that's consistent with these conditions. I can satisfy these conditions in multiple ways. So for example, suppose I have some crystal, and here I'm sketching the density of states or local density of states versus energy. And here's the bulk valence band, and here's the bulk conduction band. And in this particular crystal, it's something like a silicon surface with a dangling bond surface band that's in the middle of the gap. And on Monday, I can prepare this surface so that this surface band is fully occupied. And on Tuesday, I can prepare it so that it's completely empty. And the difference in the surface charge density between those two configurations, of course, is just 1 electron charge or 2 with spin per surface unit cell area. And if I attribute that to a bulk polarization, that means that the bulk polarization has to change by an electron charge times a lattice vector over the cell volume, which is essentially the polarization. And so any theory of polarization is required to have the property that surface charges, if we take this as a requirement that the surface charge has to be related to the polarization in this way, then the polarization has to have the property that its modulus, a quantum, is an exact thing, not just an approximate thing. Here's another second physics argument about why the polarization along two different paths should be quantized, or another way of saying it is going around a closed loop should be quantized. And here what I'm doing is making the variation of the Hamiltonian with the parameter occur not in time, but in space. So I imagine that I have a crystal. Maybe this is a one-dimensional crystal, or maybe it's periodic in the other 2 dimensions. But the main thing is that I make a long supercell of n unit cells of length A, and the Hamiltonian at the left end and the Hamiltonian at the right end are exactly the same Hamiltonian. Lambda equals 0 and lambda equals 1 are, in my notation, the same point on the loop. And then it varies slowly in between here as I go. And then I have the whole system is in a big supercell of length L. And so if I calculate the change in polarization with respect to x over the length of the cell, I can again do the chain rule and multiply out the delta, divide out the delta dx's, and I get that this is the loop polarization. So now, is this quantized exactly to be 0 or an electron charge times an integer? Well, I argue yes. Why? Because I can also interpret this integral of dp dx as the integral. So the derivative of the polarization is nothing other than minus the bound charge. I should have written rho bound here, I guess. So I integrate up the bound charge and I get a total Q bound charge. This is the extra charge that comes from the polarization variation relative to what it would have been in the supercell if the Hamiltonian were uniform throughout the entire length of the sample. And I argue that that has to be an integer times an electron charge. Why? Because if I calculate the total number of electrons in this supercell, it has to be an integer. That's a general principle of quantum mechanics of periodic solids, that if you calculate the total number of electrons in a set of filled bands, it's equal to the number of filled bands, and that is always an integer in an insulator. And therefore, the total bound charge has to be an integer, and therefore the integral of the loop polarization has to be exactly 0 or quantized in integer multiples of the charge quantum. Okay, so the form of the theory that comes out of this, one way of thinking about it is that we have a problem taking expectation values of the coordinate operator, but instead, if we take expectation values of, it's not exactly an expectation value, if we take gradients with respect to wave vector, if you think in terms of the quantum mechanical association of momentum with the gradient with respect to position, then it's plausible that a coordinate is associated with a gradient with respect to wave vector. And so this is sort of the direction that the theory eventually went. But it took us a long time to get there because we were so used to thinking of systems in which the properties of interest, charge densities, forces, energies, were always expectation values of operators. But this gradient with respect to wave vector, that's not a single particle operator. That's something else. That's something that involves a derivative with respect to wave vector k, which is sort of a parameter on the Hamiltonian of the state vectors. So the modern view of this is that we have some manifold, which is our Brillouin zone, k-space, and we have a mapping from this manifold. Each point on the manifold I have associated with that a block function, and for technical reasons we prefer to use the cell periodic block function. And then from derivatives on this manifold we construct Berry connections and Berry curvatures. And by looking at paths along this manifold, we describe Berry phases. And by looking at integrals over these things, we define Chern numbers and so on. And so this is the framework in which the theory of polarization really has to be formulated, and orbital magnetization and other things. Okay. And furthermore, a manifold lends itself to topological properties if it's a closed manifold. And the Brillouin zone is always a closed manifold. And so in one dimension, this is not the conventional way of doing it, but I've drawn the Brillouin zone as a unit circle because it really is a closed manifold. And I've drawn two energy bands plotted vertically on this cylinder. And for each one of them, I can calculate this thing, which of course, I haven't talked about Berry phases, but there it is. In the two-dimensional Brillouin zone, I can calculate Berry phases across the zone or in three because they're really closed manifold, a 2 torus and a 3 torus. Okay, so in the last part of the talk, I wanted to say a few things about orbital magnetization, and really this is going to lead rather quickly to anomalous Hall conductivity. What do I have? I've got about 10 minutes left.
Correct.
Again, what's the problem? In a toy picture in which you have magnetism, of course, most of the magnetism is normally spin magnetism, but you also have some orbital moments on atoms. And if you think of those as all localized with nothing in the interstitial region, then you can compute an orbital moment for each one and compute a magnetization. And then there's a surface current that flows along the surface, which is a manifestation of this orbital magnetization. And in insulators, this current flowing along the edge is a dissipationless current, obviously. It's not a free current. The current that flows on the edge is a dissipationless current. The magnetization is a bulk property. The surface current is given by this formula, which is the analog of the charge density being the polarization times the unit normal. And the surface current is only apparently a surface property. It's really a manifestation of the bulk magnetization. In the case of the orbital magnetization, this is really a stronger property. In the case of the electric polarization, I had to put various conditions. Here I just changed from 3 dimensions to 2 dimensions. So in the case of electric polarization, I had to put various conditions that the surface had to be insulating and perfect and so on. That's really not the case with orbital magnetization. So suppose I have a two-dimensional system here. This gray area is the bulk of the crystal. It has some orbital magnetization, and so there are edge currents flowing along the edge. If the edge current in region A is different from the region B, because I somehow terminated this edge A differently, or added some add atoms to edge A or whatever, then I would have a charge accumulation at this point, and that's not possible. I'm talking about a system in its ground state, and a ground state is a stationary state, and the divergence of the current has to be 0 everywhere in a stationary state. So both of these currents, IA and IB, are nothing other than MZ. They're really slaved directly to the bulk magnetization. So we have this dissipationless edge current that flows even if the bulk and surface are both insulating. And in this case, it's completely slaved to the bulk. And I'll discuss all of this in the context of insulating systems, but much of what I say is true of metallic systems as well, but not everything. Here's a question. Is it possible to have an insulator? Let's imagine this is a two-dimensional insulator in which you have a macroscopic current flowing through the insulator. And of course, you'd say, well, of course not if it's an insulator. But from quantum Hall effect type of physics, we suspect that the answer may not be so simple as that. So here's a simple argument why you can't have a current flowing. We have to have conservation of charge. So if there's a current flowing upwards, then we have to have some kind of circulation of current around the boundary that has the property that the current becomes stronger and stronger as I go to the left here, because it's if you think of this as rainwater coming off of a roof, then you have to have more and more flow as you come here. And so it has to be the case that the current along the surface varies as I go along the surface. But the physics of the edge here and the physics of the edge here are identical. So how can the current possibly be different? So the answer is, at some level, no, you can't have a current flowing like that. Does it help if the edges are conducting? No, not really. I mean, suppose that I put some, this is a little picture of the valence band and the conduction band projected in the one-dimensional wave vector space. And I've got a surface band that comes and cuts the Fermi energy. And you can ask, does that affect the argument that I gave on the previous slide? Does it affect the edge current that's flowing on the edge now that I have these free currents as well as the bound currents? And there's a simple argument that I won't go through in detail. If I look at one of the crossings of the Fermi energy, and I imagine changing the Fermi energy from E1 to E2 and calculating how much extra current is flowing by integrating up the extra electron states that are occupied as I change the Fermi energy, that's given here. I've got the group velocity times the number of states. I get a cancellation, and I get that the total number of the total current that flows, if I write it as a derivative with respect to the electrostatic potential, is just exactly E squared over H times the shift in the energy. So I have this sort of a quantized behavior of the conductance in the sense of extra current that flows as I change the Fermi level. And so, so that would allow me to change the current flowing at an edge. But of course, what happens is that this band crosses again in the opposite direction and I get a cancellation. And so it doesn't affect any of the argument that I gave on the previous slide. However, there is something that changes the whole argument. Suppose that I have some external electric field. This curly E in my notation is an electric field, a small but uniform electric field applied in the X direction. And now what happens is that the conditions along the edge are actually not really identical. The electrostatic potential is higher here and lower here, and then it's all the same here, and then the electrostatic potential changes along the top edge. So if you can argue that the current that's flowing on the boundary varies with the electrostatic potential, then this becomes possible. And that's the case if you have a band, a surface band that crosses in only one direction. This is only possible if you have broken time reversal symmetry. You also have broken inversion at the edge always. And so this looks like a very bizarre band structure, but it's a possibility at an edge band structure of a ferromagnetic two-dimensional system. And in this case, what happens is you only have an up crossing and not a down crossing. And it turns out that if you calculate how much current, if you assume that there's a current that is flowing in the vertical direction in response to the electric field in the horizontal direction, and the ratio of those is an anomalous Hall conductivity, then the variation in current on the edge is precisely what is needed to soak up the sheet current flowing in the bulk, if and only if the anomalous Hall conductivity is equal to E squared over H for the case of a single upcrossing band like this. So what this says is that in an insulator, any given insulator has a topological invariant, which is the number of upcrossing bands on the top surface, but then it also has to be the same on all other surfaces. This side surface has 2 upcrossing and 1 downcrossing band, and that's consistent. And the reason is that I could turn the electric field in the vertical direction, and I also have to have the same ability to soak up the current. And so basically, each 2-dimensional insulator is characterized by what we call a Chern number. It's an integer. For almost all systems, it's 0. Certainly for all time reversal invariant systems, it's 0. For all ferromagnetic systems, almost all it's 0. But for some, like the famous Haldane model, it's non-zero. So I'm almost done. An insulator can have a non-zero anomalous Hall conductivity. But if it does, it has to be this integer times E squared over H. And that's a characteristic of each possible 2-dimensional insulator. What's nice about this kind of argument, that's what we call the quantum anomalous Hall state. What's nice about this kind of argument is it also survives things like turning on interactions. So I've been mainly thinking in terms of a single particle physics up until now, but suppose I have some sample, I apply an electric field to the right, I have this sheet current flowing in the vertical direction, and now I turn on electron interactions in this blue region. Well, I'm not allowed to have any excess charge accumulating at the boundaries of the blue region, and therefore the anomalous Hall conductivity also has to be exactly this, even with interactions, and even with disorder, and even with interactions and with disorder, right? Because I can't have any accumulation of charge. This is really just a description of the ground state of some system in a weak electric field, etc. Okay, so this is my essentially summary slide. The modern theories of polarization and magnetization involve this paradigm shift away from expectation values and towards things that are based on adiabatic loops, quantities that are only well-defined modulo a quantum. These formalisms hint strongly at, but in this talk I haven't described in detail what are Berry phases, Berry curvatures, Chern numbers, and so on. In this talk, I've left out innumerable other hints at the correct physics. I think I mentioned quantum Hall physics at one point, the Karplus-Luttinger theory of the anomalous Hall effect, the Zach phase, and so on, all things that predated our, so to speak, modern theory of polarization. And of course, I think most of you are also aware that this whole theory is in some ways a precursor to the modern rage of the last 15 years, which is the theory of topological insulators and semimetals, which also depend a lot on similar concepts of Berry phases and curvatures. So with that, I think I'm out of time, and I'll thank you for your, let me stop the share. I'll restart the share if people have questions about the slides. So thanks for your attention.
Thank you, David. A real classic. We enjoyed this very much. We can take live questions, and people are welcome to raise their hands, and I'll unmute them. Or people are also welcome to write questions in the Q&A panel of Zoom, and I'll read them. So let me actually start with one from the question and answer panel. Could you comment on the possible extension of the ideas that you have shown to non-ordered systems, such as molecular liquids? Oh,
well, I really should invite Stefano Baroni and his collaborators to answer this question, because in a series of recent papers, they have addressed this problem. So suppose you have, I mean, you need to have an insulating fluid, and there are many. There are, you know, molten salts and so on, and the temperature has to be high enough that it's a fluid, but low enough that we have a well-defined electronic insulator. And then you can ask questions about what happens if you have some charged species, and you know, and it moves through the fluid. And does it carry with it an exactly integer quantized excess charge? And the answer is yes, at least under appropriate conditions. these so I would refer you to the papers of Stefano Baroni that discuss this. Essentially, one way of looking at this is to make a big supercell and take this charged species from its position in one supercell to the position in the next supercell. And there's some previous work of Andrew Rapp's group that also discussed this kind of thing, but more in the context of taking an impurity through interstitial positions in an ionic in a crystalline system, and then the Baroni papers are more about about liquid and liquid systems. So that's a wonderful question.
Thank you, David. I'll keep reading. Another question says, with the recent experimental realization of quantized adiabatic charge transport in a thowless pump, using ultra-cold atoms in optical lattices, can you now imagine research opportunities offered by these cold atom lattice systems compared to, say, ferroelectric materials?
Yeah, so the cold atom systems are fascinating. You know, I think it all depends upon where you want to go with your research career. So in terms of fundamental physics, the cold atom systems are fascinating. They're very engineerable. That is to say, you can construct many systems that you couldn't possibly have the same freedom to construct out of real material systems. And you can explore, you know, flow K systems and all kinds of things that would be difficult to do in the same way in a material system. On the other hand, you know, many of us are really materials physicists at heart, and we really want to understand systems of real electrons going around real atoms in real materials. And so I think both things are fascinating. And I expect that the you know, what can be done with cold atoms will continue to inform what our understanding is of materials. Yeah, I don't know what more to say about that.
Thanks. Thanks, David. I'll keep reading. Maybe I'll summarize the next question. It says, you know, when we calculate the polarization at, say, complex interfaces, this is often done using atomic displacement and Born effective charges. And so the first part of the question is, how accurate is this approach? And then the second part of the question ask, is this also possible to be used to estimate flexoelectric polarization and flexoelectric coefficients? Well, it's a bit different, the second part. So maybe I'll read it better. So maybe the first part of the question, how accurate is this model of effective charges, time displacements?
Okay, so, you know, if I go from configuration A to configuration B, and I go along a path, and at each point of the path, I recalculate the dynamical effective charges, and I integrate up the, you know, displacements of atoms times their dynamical effective charges evaluated at that point on the path, and I do the integral along the path, I get exactly the right answer. If I take the dynamical effective charges at the starting point and freeze the, you know, keep those values and then multiply them times the displacements and going from A to B, I get a pretty good approximation. If I, you know, if I just kind of look up from the literature some reasonable estimates of dynamical effective charges, let's say in barium titanate, you know, the titanium is anomalous, so let's put 7 or something. I even then I get kind of reasonable values. I like to recommend that those estimates are extremely useful in situations where you might have some doubt about which is the right branch choice of the quantum. You know, those kinds of estimates almost always put you in the neighborhood of the right branch choice. So I would recommend it for that.
Yeah.
And for some purposes, if you just want, you know, something that's accurate to 10 or 15%, it may be good enough. Yeah.
Thanks. And in fact, the context of this was, you know, to do it maybe at super lattices where you would use bulk effective charges.
Yeah.
Because the second part of the question asks, can we do the same for ferroelectricity. That is, can we use flexoelectric coefficients computed for bulk materials and the strain gradient found in the superlattice? So the question is, how do we do?
Yeah, I think so. And again, I mean, the flexoelectricity depends on more than just dynamical effective charge, more than just dynamical dipoles. It also depends upon dynamical quadrupoles, and there's a electronic piece which is rather tricky to calculate. But again, I mean, I think it's, you know, if you can calculate these things for small unit cells and then use them as an approximation of what happens in a big supercell, that's an entirely reasonable approach.
Thanks. I think I have a last question myself, and then we'll go to a pause. But you know, when you started with this classical picture of charge densities, it reminded me also of, you know, density functional theory, that is a quantum theory based on the charge density, and the so-called GGG theorem that says that actually in a solid, you know, what we have is a functional not of the charge density, but of the charge density and the polarization. So we always think of charge density, but that's not enough. The polarization is there. And so my question is, how come we have, you know, always been able to predict the properties of ferroelectric materials, the polarization in solids, using exchange correlation functionals that, you know, are do not have the polarization explicitly present. They are just exchange correlation functional of the charge density.
Well, yeah, I think the short answer is that there could be a very long answer. A related question is, if you calculate the polarization in exact cone-sham theory, do you get the exactly correct polarization? And the short answer is not in general, but then you can ask, and I have a paper about this, there are some conditions in which the answer is yes, and other conditions in which the answer is no. But anyway, then you can ask, if you calculate the electric polarization within our typical exchange correlation approximations to cone-sham theory, do you get the right polarization? And you know, that's hard to answer, but our experience seems to be, you know, that it has the same kind of accuracy as other quantities, like kind of 5% accuracy, 5-10% accuracy, similar to what we would get for computing, you know, phonon frequencies or anything else. And so in practice, it seems to be that we don't have to worry about this. I think the subtleties of the distinction between our practical implementations of cone-sham theory and exact cone-sham theory are probably larger than the issue of including the polarization into the functional.
Okay, David, thanks a lot. I think you know, we'll stop here for a pause. Thank you again very much for this beautiful talk. We all go for coffee. And then we meet again in 7-8 minutes at 4:10 Central European Time for the talk of Raffaele Resta. Thank you again, and see you everyone in less than 10 minutes. Okay, so welcome back everyone. And so this is for me a great pleasure to introduce Professor Raffaele Resta from the University of Trieste, that will be the other speaker in this CECAM and MARVEL Classic. Raffaele holds a laureate degree from the Scuola Normale Superiore in Pisa. That's the Grande École for those that are familiar with this concept in Italy. And just after graduation, he became an assistant professor in the University of Pisa, where he stayed for a few years. His bio mentioned also sailing semi-professionally, so we'll ask later more about that. He moved to the newly funded International School for Advanced Studies in Trieste, CESA, in 1981, and he has been a professor at the University of Trieste since 1994. Raffaele is a fellow of the American Physical Society, has been a divisional associate editor for Physical Review Letters, and also has been a frequent visitor to Lausanne. I remember exactly at the same time studying intensely is lecture notes for what was called the troisième cycle. That was a special series of lectures given here to the physics students. So with this, give me great pleasure to introduce Raffaele for the second talk of this CECAM and MARVEL Classic. And Raffaele, the floor is yours.
Thank you. Let me see here. File. Open listen file. I have to share the screen. Am I already sharing or not?
Not yet.
Shit, I opened the file too soon. Let me see. I have to share the screen here. Share screen.
Let me read your title.
Fine. Then I click here.
That will be electric polarization.
I open, and now I have this. Okay. And I enter full screen.
Super. So it will be electric polarization, orbital magnetization, and other geometrical observables.
I believe I'm set. Okay.
Super.
Okay. Fine. So you may notice my affiliation also has a minor affiliation with San Sebastian. Before the pandemics, I used to spend there a couple of months almost every year. We'll see what happens when the pandemics ends. And let's go back to the two main material properties that David addressed. One is, I have this, one is polarization and one is magnetization. And a very trivial definition, which is given even in textbooks, is the dipole moment per unit volume, the orbital moment per unit volume. And of course, this implicitly requires a bounded system that is a finite crystalline, ideally even macroscopic, but definitely bounded. And of course, this cannot be used in condensed matter physics, because in condensed matter physics, we use Born-von periodic boundary condition. The problem, as was pointed out by David, is the operator R. Operator R is not an operator in the Hilbert space of periodic boundary condition, because it maps a periodic function into a function which is not periodic. So you cannot do in general initial solid state physics. Furthermore, those integrals are dominated by surface contribution, of course, because there is an extensive contribution from the surface. We divided by volume, you have certainly a non-negligible contribution by the surface. So if I cut a piece of the material in the bulk, really I cannot tell what polarization is from those two formulas. And this is the reason why the problem was so difficult. Condensed matter physics requires a completely different definition. And even today, most textbooks are plain wrong on the issue. They say, and maybe when we have the final part in the interview, we can say more about that. But the message that polarization has nothing to do with the density has not percolated into the literature. So our students still learn something which is conceptually wrong. Now, these are the formula. David, I will explain below better what are the symbols. You see there is no position operator. There is no magnetization would require a position and a current or a velocity. There is nothing like that. In particular, polarization, you see, this is the formula which was flashed by David earlier, is just the derivative of the periodic part of the block orbitals. It is important to add the nuclei because even for a finite system, the dipole is well defined only if the system is neutral. So you have to compute the dipole by considering both the charge of the electrons and the charge of the nuclei, which must compensate. And in fact, this compensates. This part is classical. And the fact that the polarization is a well-defined multi-valued observable, as David has emphasized, it is only true when you consider both terms together. Otherwise it's no longer true. So both terms together, you have the polarization is defined modulo a quantum. This was the theory which came out in '92, published in '93. This was the most exciting year of my professional life, of course. But many years afterwards, it is more than a decade afterwards, we teamed up with David and two very good young people, and we made the theory, the apparently analogous theory for orbital magnetization. I say apparently analogous because, as you've seen, the problems are the same. Going back to, I will not go back the slide, but in the previous slide, you see they are generally really very, very close friends, the two observables. But then we discovered, and we started by analogy. But working on that, we discovered that they don't have really the same property. We have said, since David had not said what means geometrical, why these two formulas are geometrical. They are geometrical, roughly speaking, because the derivative of the wave function. But if you look at polarization, and you go back to what you learned in elementary quantum mechanics, in order to have an observable in quantum mechanics, you need to have an operator. You have to invent an operator, to define an operator such that what you observe is the eigenvalue of the operator, is the expectation value of the operator or the like. Here, there is no operator. It's only the wave function, no operator at all. And still, this is observable. And in fact, this is a very phase, as even in the title of our series. And if somebody asks me what is the message, in a few words, the message of the very famous paper by Michael Berry in '84, I guess, I would say Berry proves that in quantum mechanics, whenever you can build a gauge invariant expression, this in principle is measurable. So here we have a gauge invariant, we have a phase in quantum mechanics were neglected because they are in general not measurable. But if with the phase you can build up something which is gauge invariant, then this in principle is measurable. And this is precisely the case. We have a very phase, a phase. It's not clear to you why this is a phase, maybe to some of you, but in some sense it is clear. It depends only on property of the wave function across the brilliant zone. So if you know the wave function across the brilliant zone, you know the polarization, you don't need any operator. And orbital magnetization is a bit more complicated. So we say both are geometrical because both have a derivative of the block orbitals, periodic block orbitals. Notice that here there are two and here there is one, but they are geometrical in this sense because they have in common this feature. One important difference, just to start with, is that polarization is defined in insulators only. Orbital magnetization is defined also in metals. And both are geometrical in this sense, but you would see they are rather different. Here, the ingredient, besides the derivative of the orbital, you have also Hamiltonian and eigenvalues. But David, and I will speak afterwards also of the anomalous Hall effect. In the anomalous Hall effect, you don't have the Hamiltonian. So you have something which has in common with polarization the fact that you only have the derivative of the orbitals in order to define an observable. Now, these are similar, but you may, now here is the plan of my lecture. I will try to touch some of those. That is, first of all, I see this part one will be within band structure theory. Band structure theory, I mean crystalline systems of non-interacting electrons in mean value sense. That means either Hartree-Fock or Conchamp. So our orbitals are either Hartree-Fock and Conchamp, and the interaction is kept only at the mean field level. For those, there are several observables over the years. We understood that they have a geometrical character. Here I've listed a few, and we discuss some of them. I will not all of them. Then there are other. We can go beyond band structure theory. One possibility is you have a disorder or a correlated system where you need a supercell. There is no longer a block vector. Routinely, calculations are computed with a gamma point only, so you only have periodic function, okay, or if you want only 1K, but yet in this case you focus on systems which are macroscopically homogeneous. I will say nothing of this part, which there have been results in the last almost 30 years, because the theory of polarization, as I said, starts in 92. That means we are 30 years after that. There are results here. Not all of them, but some of them have a definition for both systems. And the third, in which I will say something, if the time remains, is instead the reverse. That is, you have a system which is macroscopically inhomogeneous. Suppose you have a superlattice or a heterojunction. You have a system which is partly different polarization in different size, or partly metallic, partly insulating, or whatever, or different orbital magnetization. And you may ask, can you define a density? Can you identify the intensive property you are looking at? You can identify by means of a density in a part only of the system. Clearly, with the K vector, you cannot do, and not even with the supercell. You get, if you deal an heterojunction with the supercell, what you get is an average property. You don't have a spatial resolution. You don't have the resolution to say that. So we have, in the last years, I worked mainly in this. I will tell something if time remains, but if time remains, because I want to go very slowly and to be possibly pedantic. And so I can cut easily with no harm part of what came then. Now, going back to, so the outline is here. So the outline is here. I will convince you that the geometrical observables are very different between them, and in particular are partitioned into different classes. What I call here class 1 observables. The bulk value is the final modulo of the quantum. The quantum David was speaking about, which in dimensionless units, I would say this quantum is 2 pi. Then you have to see what are the dimensionless units. And then there are the class 2 observables, which instead are single valued and exempt for any quantum ambiguity. And as David has shown, orbital magnetization is in this class. The anomalous quantity, all conductivity is also in this class. Then, and this will exhaust a large part of my time, focusing on some class 1 observable and some class 2 observable, always at the band structure level in the sense I specified. And then, if time remains, I will show some only class 2 observable may have a local definition, local description, and density, an associated density. And we worked on 3 of them, and I have some slides about that. Now, let's go back to what I've shown before. The electronic part of polarization is this integral, which I've said before is essentially a Berry phase, and is the integral of a quantity which is called the Berry connection. This Berry connection is a geometrical property. It is gauge dependent. What does it mean, gauge? Because we are speaking of gauge dependence, gauge invariance. Now, gauge, when one learns at second year gauge, you change the gauge and you change the vector potential with uncertainty Hamiltonian. For a given magnetic field, you have a wide choice. And of course, the fact that in quantum mechanics you have such kind of exotic effects comes from the fact that you cannot write a Schrödinger equation directly in terms of the fields. While in classical mechanics, you write Newton equation just in terms of the field, then vector potential may disappear. But in quantum mechanics, you cannot write a Schrödinger equation with the field. Necessarily, you have to choose a gauge, and in that gauge, you can compute the wave function. Now, the wave function depends on the gauge. But and the Hamiltonian depends on the gauge, and the wave function depends on the gauge. Once you have fixed the gauge Hamiltonian, you remain with another freedom, is to have an arbitrary phase factor in front of each u vector. So you have a u vector. If you multiply u vector for any phase factor depending on k, constant in space but depending on k, this is still an acceptable equally good wave function. And so this, even when you have fixed the Hamiltonian, so even when we have chosen the electromagnetic gauge, you still have an arbitrariness in this quantity. But this arbitrariness disappears when you take the loop integral essentially of this Berry connection, but it is a phase, so in appropriate units it is arbitrary modulo 2 pi. In units of polarization it is arbitrary modulo a quantum. The magnetization doesn't have this arbitrariness. Here on the bottom I explain what are the notation. U has already been defined by David. The Hamiltonian HK is just the Hamiltonian which acts on the U, not the one which acts on the psi. You have the Van Dykstra Fermi level, and you notice that in this Hamiltonian there is something which resembles a vector potential, and the Hamiltonian, like a vector potential, is a vector potential which does not depend on space, does not depend on time, so there is no electric or magnetic field associated, but still mathematically enters the formulas as vector potential. Now you may ask, we were happy and say we have found something similar. Well, it's not so similar because of the reason I say, but really similar. And I will show they could not be more different. That is, polarization makes sense in insulators only. Orbital magnetization makes sense in both insulators and metals. The integrand is gauge dependent in the sense I've said before for polarization. It is gauge invariant instead, in the sense I said before for the magnetization. Is the integral of 1/4. What I mean 1/4, here I will use a rather sloppy definition. A 1/4 is a differential form which has only one derivative in this sense. One form in general would have one differential and one derivative, and when you include the coefficient of the form times the differential, you have a dimension. But of course, this is only true in one dimension, not in three. If you integrate in three, the differential is so let me say very sloppily, a one form has only one derivative of a function, a two form has two derivatives of a function, and this, as you will see, is a very strong difference. Then at the most fundamental level, polarization is a one-dimensional phenomenon. I can define for sure polarization of a linear polymer, and I can also imagine that a solid is built as an array of interacting polymers, so it is one-dimensional. And instead, magnetization is two-dimensional. As a minimum, you must have electrons two dimensions and magnetization normal to this direction. The bulk value of polarization is multiply valued, and instead the magnetization is single valued. Now, if you think with the boundary, you can alter the value of the by a quantum, but can be altered by a quantum. Instead, if you think with the boundary, there is no way of altering the value of magnetization. So these are extremely opposite properties. Why? This is prototype of class 1 or observable. There is another one, which is a very close relative of this, and there are, to my knowledge, no other ones known. And instead, in class 2, there are several, in particular, orbital magnetization and anomalous Hall conductivity, the ones which we will address later and also addressed by David. Now, modern mathematics knew this very, very long before physicists, as often happens. That is, the modern differential geometry developed in first half of the 20th century with results by Contraghi and Cartan-Weil, Chern-Simons. In particular, the most important result by Simons came out, I guess, in 1974, the Chern-Simons famous paper. And they studied those forms, so one forms in dimension 1, two forms in dimension 2, three forms in dimension 3, and so forth. And then the main message to learn from this mathematics is that the 2n forms, so that means forms and the 2n minus 1 forms, that is even and odd dimension, they behave in a quite different way. And in particular, if you focus only on the antisymmetric forms, so the forms where the coefficients are antisymmetric, a function of the coordinates, In the symmetric case, you can define in dimension 2n, you define what is called the first chair form and also the first chair number, which is in our domain becomes a tk and n invariant. And David spoke about that. Instead, if in 2n minus 1 dimension, there are completely different kind of forms, but they are related. That is, in the simplest case, if you go to 1 to 2, you take the first Chern-Simons form, you take the curl, and you get the first Chern form, and so on, going on with dimension. Now, in physics, we have only 3 dimensions, at most 4 if you wish to have the time, but mathematicians, of course, they go to n as high as you like. And this is the main reason, essentially, why polarization and magnetization are so different. Because one is a 1-4, the theory needs a 1-4, the other one needs a 2-4. So this is what I've shown before, is the quantity which you have seen already many times today, and this is a Chern-Simons 1-4. More exactly, for a mathematician, a Chern-Simons 1-4 will have the decay and to multiply, and we will only be addressed in one dimension. It will not even have the I, because with the I it becomes real, without the I is purely imaginary, but there's no problem. If you take the curl, just the regular curl, a normal curl, you have this, and this simple formula is written for only one band in one dimension, and this is written for only one band in 2 dimensions. The orbital magnetization obtains, as you have seen before, from a 2-4, which is closely related to this one. This one, as it is, without modification, is the one which gives you the anomalous Hall effect, both and also the quantized Hall effect in non-anomalous. I would say the quantized Hall effect, the anomalous Hall effect, and the quantized anomalous effect, all kind of Hall effect in a sense. But now, since we live in a 3-dimensional world, you may ask, does a Chern-Simons 3 form have any physical meaning? And in fact, some very clever people found that it does. And it has the same properties of polarization. Now, what does it mean that is the final module to pi? In some sense, I've been explained already by David, but I want to elaborate more on this. The bulk polarization is a lattice. This was specified. This is a second. Notice that this is a second of the 2 famous papers by King-Smith and Vanderbilt. There is a King-Smith and Vanderbilt first, and then Vanderbilt and King-Smith is the second. In the second, they say that polarization is a lattice, not a vector. And what is important, whenever you have a bounded sample, the value of P is ambiguous until sample specification is, sample termination is specified. So when you truncate a crystal with a given crystal structure, it is nature who chooses which is the value of polarization. It is amongst the values permitted by the bulk theory, it is the value that makes the energy minimum. You will see an example of that. For a 1-dimensional system, the polarization is the dimension of a pure charge because it is a dipole over a length. And the formula is particularly simple. It is E over 2 pi times gamma, which is a phase, which is the final module to pi. And this must include the nuclei, as I said you. And now suppose we have an inversion symmetric material, an inversion symmetric polymer. Then you need P equal minus P, but since polarization is a lattice, you only need the lattice to be symmetric, not really the value itself. And the lattice could be symmetric in 2 very different ways. One is polarization is 0 modulo E, the other one is 1/2 modulo E. And this is mapped 1-to-1 into the additive group of the integers modulo 2. That means it is a Z2 observable. Arguably is the simplest and more elementary example of Z2 invariant. Topological Z2 invariant. We will explain also why it is topological. But we made the simulation in polyacetylene several years ago with Roberto Carr and Konstantin Kudin in Princeton. And just to demonstrate, this was published in General Chemical Physics because this was to improve the literacy of quantum chemistry about this. So the paper was written avoiding very phases and exotic stuff. Just we took 2 very long molecules. This was polyacetylene with some termination, and this was the same polyacetylene with different termination. We noticed that the bulk is centrosymmetric, so the theorem applies. This must be, the polarization must be either 0 modulo 1 or 1/2 modulo 1. But of course, whenever the realization is finite, the two molecules are both asymmetric, and so the dipole will be not zero at finite length. Quantization only appears in the long chain limit. And this is the result. So the constant including used Gaussian code. The Gaussian code, you get the coordinates and some information about the basis set, and the Gaussian code tells you what the dipole is. The dipole per monomer was here. And since the lattice constant was 4.7, you can easily see that for this material, the polarization is either 0 or 1 of one charge. Why? Because polyacetylene is in Z2 even category. That means polarization, if you do a very phase calculation and we include the nuclei, polyacetylene polarization is 0 modulo 1. Now, what are the other class? Well, it is like this. Polyacetylene you can simplify with this simple sketch. Also, if you take a series of hydrogen molecules on a row, you get the sign, and polarization is 0 modulo E. Instead, if you model a ionic crystal, you have a plus and minus, plus and minus. This is the case, the other case. The invariant is topological, that is, it's robust by continuous deformation of the wave function, so you can switch from a simple tight binding Hamiltonian to a full interacting, correlated, whatever Hamiltonian. This invariant cannot change insofar as the system remains insulating. So it's independent of the theory level, and there was something earlier which was due exactly to the same reasons, a very, very important paper by Schrieffer and Higger about the quantized soliton exactly in polyacetylene. Now, there is a simple exercise that if you take the simplest model of this, that is one side, one orbital per side, one-dimensional tight binding, you have two parameters. Here you have alternating hopping T and T prime, and if you want to preserve centrosymmetry, you need to take the on-site elements constant or even 0. Instead, here, if you want to preserve inversion symmetry, you have to keep constant hopping and make alternatives. This is protected by inversion symmetry, sorry. And you can try the exercise because it is diagonalizing a 2x2 matrix. You realize that if you try to transform with continuity the Hamiltonian which gives this into the Hamiltonian which gives this, necessarily at some point you close the gap. If you want to keep it centrosymmetric. So if you keep there is no way of keeping a material centrosymmetric and moving from and transforming with continuity this situation into this situation without closing the gap. Now we need, in order to go ahead, we need to do something a little bit more sophisticated. This is the connection, but you have off diagonal terms. So the diagonal is the very connection. You have a non-abelian matrix. And now, as I said, what is the tree form, which is the polarization one-dimensional system, including nuclei, can be the electronic term. Let's say, forget about nuclei, can be written like this. Here, I include the differential in this formula. So, and this is exactly a Chern-Simons one form by definition. Now, the Chern-Simons three forms, if you go to Wikipedia, they have a very nice compact simple form. If you convert the mathematician formula into Brillouin integral, you have this rather ugly thing. This also have to do that mathematicians use very synthetic, very compact notation, but this is nothing new with respect to mathematician new since 1974. This is something like a higher order periphase, because this is an angle. This is something which is dimensionless, and it is defined modulo 2 pi. And there are three derivatives, you see, because you have the connection as one derivative, the connection as again, so you see there are three derivatives. So it's a tree form. And does theta have the physical meaning? The answer was found in 2008 by Chi, Hughes, and Zhang. So this is as a mathematical meaning. What is this meaning? Well, the important point, besides the meaning, I would say, in my view, more than the meaning, is important what happens when you have either time reversal symmetry or inversion symmetry, because like in the case of polarization, analogously to the case of polarization, it is only possible to have 0 on pi modulo 2 pi. And this, the reason why this is very, very important is because it is a way of classifying the three-dimensional topological insulator. If it is even, so if this number is 0 modulo pi, it is trivial. And if it is Z2O, it is a non-trivial topological insulator, which is called a strong topological insulator. This is the case where it is time reversal symmetric. You can also instead take only the case with an inversion symmetric, and this is called axial insulator. As far as I know, this has not yet been discovered in synthesized. Instead, the strong topological insulator has been synthesized. David has some papers about that, so maybe correct me if it has been found, the axial insulator, but I think it has not been found so far. Now, the physical property associated is not really interesting. It's not really interesting because it's only one part of the effect, and experimentally would be very difficult to isolate that part of the effect. So I will not tell what the physical effect is. But then you see the table of all the class 1 observable we know of. There are 2 angles, both the final model 2 pi, both in insulator only, and all have this form general, where the integrand is a gauge dependent 2m-1 4. The bulk value is defined at modulo 2 pi. For a bounded sample, the actual value depends on termination. And if you have some protecting symmetry, both become topological invariant. Now let's move to, I have less than a minute, so let me go a little bit fast. The example which are exempt for ambiguity, here is my table, all of them. I will discuss only anomalous Hall conductivity and maybe orbital magnetization. They have this structure. The observable is again the integral of a form, but the form is a 2 form, not a 1 form or a 3 form. There is no modulo 2 ambiguity. For a bounded sample, the actual value is independent of termination. You may tinker with the boundary as much as you want. You cannot change the value of this. And you may, and also let me anticipate, since I will not show in this talk, they admit a local representation. They admit a density. So you can forget about the K-vector and you can define them even if you have a homogeneous system like an heterostructure, while you cannot do that for polarization. Now, you notice in this table, on the same row, I have actually the same differential form, symmetric, antisymmetric part. And there are also 2 sum rules. I will not explain why a sum rule is actually, sum rule is an excitation property, is not a ground state property, but at the end, if you integrate over the frequencies, an excitation property becomes a ground state property. Now, again, there are T odd and T even. We notice that the T odd, essentially, you have the same formula for metal insulator. They don't care whether you have metals on insulator. They are actually the same formulas. But instead, they even are different. One is defined for insulators only. One is defined for metal only. It is in insulator, the weight is trivially 0. And in the sum rule here is infinite, formally diverges. The reason has to do with whether there is or no a Fermi surface. Fermi surface make this, but this Fermi surface is ineffective on the left hand, on the antisymmetric. Now, it is possible to cast them in gauge invariant form. This is a projector on the U states. Of course, only determines the occupied manifold of block states, doesn't care which state are occupied, doesn't care about band crossing and the like. And since the quantity we are looking for are gauge invariant, they must be expressible as derivative of decay. And since the class 2 observable are rooted in 2 form, all observables in the class must have 2 derivatives of T. And in fact, it's here, orbital magnetization. This is the formula shown before, the formula we arrived at in 2006, and the formula you find in David's textbook. But it can be shown with some work that it can be written in this way, where only gauge invariant quantities enter, that is the gradient of the projector. Now, let's go to the simplest of all. The simplest is there is no Hamiltonian inside. You simply take the curl of the projector. More exactly, you take the most general tensor, which has a symmetric and anti-symmetric part. The symmetric part is the metric, which is also important, but I will not discuss here. We focus on the anti-symmetric part, which is the Berry curvature, and it is the gradient. It is the curl of the connection. Well, the symmetric part, well, I can do this. In the year 2000, Sousa, Wilkins, and Martin proposed to discriminate insulators and metal looking at this integral. This integral, of course, is finite in any insulators, it diverges in all metals. And in the case when it is finite, it is a measurable quantity. It is a gauge invariant property, of course, and it is a ground state. It can be shown it is a ground state property. So in order to measure, you don't have a probe acting on the ground state. You have to measure conductivity of these insulators as a function of omega. As a matter of principle, you have to integrate. But finally, this is a ground state property, just the Brillouin zone integral of the quantum matrix. And some of you know that this matrix enters the theory of Marzari-Vanderbilt one-year function, very famous 1997 paper. It's a gauge invariant spread. Now, in insulators, I consider metals as well. So this is the Berry curvature, even for a metal. I sum up to the Fermi surface the Berry curvature. And the intrinsic Hall conductivity can be written in this way, in 2 dimensions, in 3 dimensions for insulators, for metals. And when you go to the special case of an insulator in 2 dimensions, you have an integral over the whole Brillouin zone. And this, you can try here, you notice here there's an H bar, but it becomes an H with the count over factor pi. Finally, what is in red is 1 over 2 pi times the integral over a compact manifold of the Berry connection, Berry curvature. This is an integer because of a famous theorem due to Chern in 1940, I guess, or at least in 1940. So this is a topological integer. Now, in metals, you have the anomalous effect exists in metals. It was discovered by Hall himself in 1881. There are for sure intrinsic contribution. The theory was controversial until 2000. It was, despite the pioneering work by Lottinger, it was assessed without no doubt that there is a geometrical contribution only in the early 2000s. And in fact, with hindsight, it is just the same formula as for insulator, just adopted to metals, where it is no longer quantized, but still has the same effect. Now, as I said, I have no time because I'm running over time. So the local network of class 2 observable I will not discuss, and I will go to the let me discuss at least this. Local network means that you have something like that, and if you know what happens here, only here, can you tell what is the observable? And the answer is yes, if it is orbital magnetization, yes, if it is anomalous Hall conductivity, no, if it is polarization. Because polarization, if you know what happens here, you only know polarization modulo a quantum, and the actual value of the quantum is fixed by what happens at the boundaries here. So I pursued a program which I started in 2011 with Raffaele Bianco, and then I continued with my other very talented student, both very talented students in following years, to really to find the form of this observable and to demonstrate that they work correctly. But I will show you nothing of those results, and I will jump to the connections. Maybe this is useful. Orbital magnetization, this is the formula I've shown earlier. We could demonstrate it can be written in this alternative way. The integral is the same, so it's in spirit is similar to integration by parts, but the integration by parts reshuffles the integrand in different spaces such a way that if you use this, a density. You can look at this as the integral of a density. This cannot be looked at as the integral of a density because it's dominated by what happens at the surface. Okay, and then as I promised to go to the conclusion. So the conclusion is that the geometrical nature of several intensive observables have been elucidated over the years, even beyond band structure theory. So that means even beyond crystalline systems in a midfield scheme. And then when you specialize to the crystalline systems, so you specialize to what I call band insulated band metals, in short means what I said before, you have, we discovered that there are two very different classes, which have very, very different features, and some features hold only for what I would say essentially one-dimensional observable or essentially three-dimensional observables, and the other properties, very different, which I focus on, only hold for a system where in very essence, the phenomenon is two-dimensional and they're based on twofold. And with this, I thank you for your attention, and I'm ready to answer your questions.
Thank you, Raffaele, for this very beautiful and insightful talk. So as before, people are very much welcome to write questions in the question and answer, or also to raise their hands, and then I'll unmute them and they can chip in. I'll also start from the question and answer. Thank you for the very nice talk. My question is, if R is not a proper operator in a periodic system, how should we interpret the exponential factor e to the I k r appearing in block functions? And the second question is that in what circumstances should we use non-abelian Berry connection or curvature?
Well, and let me answer to the first, then I missed the second. The answer to the first is you have something which is not an operator, but then if you take exponential I, this quantity which is not operator becomes an operator, and which is in particular, if you forget about the k, but if you have a periodic boundary condition over length L, then of course x is not an operator, but exponential I x times time 2 pi over L, this is a periodic function. So some combination of an illegitimate operator can become a legitimate operator. This is the answer, I would say. And let's say what the second part of the question?
So the second part is under which circumstances should we use non-abelian Berry connection or curvature?
Well, for sure, we use numerically. That is the computer codes. Actually, the computer codes which compute polarization do not distinguish bands. They only deal with all of the occupied bands together. It's not important when you have a band crossing. It's not important where to continue in order to define the connection. So it means the algorithms which are commonly used in the electronic structure code, in fact, are non-abelian. They compute eventually. So they deal with non-abelian phase. Actually, what they only need is the trace of those quantity, but they are in the non-abelian. Then, if you want to go instead to the topological to the Chern-Simons form, then the Chern-Simons invariant is non-trivial only if you have a non-abelian, only in the non-abelian case.
Thanks, Raffaele. I'll keep reading, but again, people are really welcome to raise their hands. I saw a lot of friends and colleagues over there. And so another question says, class 1 and class 2 observables, are these comparable when a global gauge can be defined via Stokes' theorem?
Yes, in a sense, yes. That is, the observable of class 1 in general, particularly in the topological non-trivial cases, a global gauge cannot be established. That's the point. You need to have an obstruction. So for class 1 and class 2 observable, in the non-trivial cases, you need to have an obstruction. And class 2, instead, the obstruction have no role, essentially.
Thanks, Raffaele. And another question, what about the real part of the Berry curvature? Is there any meaning to it?
No, the Berry curvature is real in the sense it comes from I times the asymmetric part of a matrix, which is purely imaginary. I say, but I know, I understand what you're saying. We have the metric curvature tensor, so the real part would be the metric, in fact. The real part is the metric, and the imaginary part is the curvature.
Okay, thanks. Now, another question. A rigorous definition of the local polarization doesn't work, but local dipole models have been very effective, say, in empirical models of water using exactly a local molecular dipole. So can you comment on the limits when, say, a local dipole picture breaks down?
Yes, the limit is in whenever you have a bound, water is a rather strange molecular liquid, so water is special for several reasons. But if you have a molecular solid or a molecular liquid, you actually have an interstitial region around, which is almost, you can assume it is empty. So you can do what David has shown in his picture with his small dipoles. So you have molecular crystal, the dipole of a molecule is defined in some sense with a good approximation, and also in a liquid. Water is a bit special because of the water is the most complex liquid of all. Because of the hydrogen bond, this picture is rather complicated. And in fact, we had a few papers in collaboration with Roberto about on the infrared spectra of ab initio infrared spectra of water. The first paper, by the way, has been done on this line, has been done by Michele in Silvestrelli and Bernasconi in 1997 or 1998. And that was done with a single point Berry phase. I've not spoken about that, but maybe this I'm moving a little bit into the next section, but I think is a good point. Silvestrelli called me or sent me an email. Can we compute the Berry phase with 1 point? Because they were running single gamma point Carpari simulation. They wanted to compute the infrared spectrum in that way. And I answered, no, we cannot, because a phase with 1 point has no meaning, at least 2. And then I went home, and then thinking, when I came back to the office, I had a very small type binding code. I was showing that if I have 1 cell and 8 points, or a supercell, double supercell, 4 points, quadruple supercell, 2 points, and so on, I got the same result with the computer accuracy. And then I came back. I had the do loop. I made the do loop going to 1 point, and it was working. But the puzzle remained. So the paper came later. I was struggling probably almost 2 years because the analytical proof for that result was not so easy. And when I arrived at an analytical proof, that came through a more general theory. So with a special case of a more general theory, maybe you know my paper on the single point Berry phase. But the single point Berry phase, I had a computational experiment which told me that is correct. This is important, the way we work in computational physics. You have an experiment and you don't know the result. You discover the result, and then you have to understand why you have that result. Yeah.
Thank you, Raffaele. And maybe the last question to keep ourselves on time on this more scientific part. Polarization and magnetization are related in relativistic theory. So what about Lorentz invariance?
Well, we are doing non-relativistic quantum mechanics and Schrödinger equation. So I have in materials we have to do that. In materials, the Lorentz invariant, still you have the material must be at rest, or you have to be in the reference frame of the material. So we are not doing electromagnetism in vacuum.
But I guess I'll confess my ignorance then, because how can you combine, you know, one form and two form into, you know, a single quadrivector or whatever into a single relativistic?
Well, Chern-Simons theory are by now a staple in high energy physics when you include the time, and they do that. They do that.
Okay, Raffaele, I also thank you very much. So what I would suggest is we stop here, the more scientific part of the talk. That was wonderful. I also suggest that we take a 4-minute pause just to give everyone, you know, sort of a little bit of a pause. And then I would say, with this beautiful picture, we start again in 4 or 5 minutes, and we do, you know, more, I would say, relaxed and general conversation about the field, how it started, and, you know, I'll ask some questions about the development of what has happened. So thank you again, both of you, very much for this, and see you, I would say, in 5 minutes sharp. Great. I think this is meant to be also more informal, so I think I'll just remove my background. So welcome back, David and Raffaele. So the spirit of this classics is also to give new audiences a sense of you know, what it was to develop this kind of science and this research. So actually, one thing I have asked both David and Raffaele is to give us some recollections on how all of this started, and if they can help us, you know, go back to the, you know, early and I would say fairly pioneering years of electronic structure research. And I think David might even have some slides of a more light-hearted nature, and maybe Raffaele also has some. But maybe David, you could start and, you know, share with us in general your thoughts going back, you know, a few years. Let's put it this way.
Okay, thanks. Yeah, I really appreciate the opportunity to do this. This is fun. So I just have a few slides that I wanted to put up here. First of all, I just, you know, there are so many seminal contributions that came before that sort of laid the groundwork. I think people know about Walter Kohn's work on the theory of the insulating state and so many related things. Eugene Blount at Bell Labs struggled with how to tame the position operator in the block representation and did so in his own way. Joshua Zach basically had the Berry phase in his hands, but was using it in a different way to characterize symmetries of band structures. David Thouless, of course, did seminal work on the quantum Hall effect and adiabatic charge transport that we should have been paying more attention to, but weren't really paying more attention to. But, you know, none of these people, you know, solved the problem of computing polarization in ferroelectrics, and our community did. And why is that? I just want to make the point here that, you know, when you're in a computational community and you're doing calculations on real materials, barium titanate, and there's actual interest in understanding polarization in these materials, and we know how to calculate A, B, C, and D, and then we find that we don't know how to calculate E, it's really annoying. And so that's how it was in the early 1990s. We actually knew how to calculate derivatives of polarization with respect to, let's say, atomic displacements, that was dynamical charges, or electric fields, that's the susceptibility. The linear response, you know, theory was well developed, but to calculate polarization itself was a real challenge. So I think really the necessity of coming up I mean, to really understand something, if you can implement it in a computer algorithm to actually calculate it, it means you really understand it. And so that's sort of what happened in our community. I want to flash up the King-Smith Vanderbilt paper. Some people asked me why this didn't get into PRL. It was certainly submitted to PRL, but I have to admit, in retrospect, it was rather dryly written. I think in part, this was Dominic, I think, didn't want to be too aggressive, but, you know, maybe we should have written the introductory paragraph to say this is a paradigm changing this, that, and the other. But it was, in this paper, we derived formulas for calculating changes. The method is suited to first principles calculations, blah, blah, blah. So I think it's on us in a way that, but of course, this paper is now extremely highly cited, so it got its due in the end. I also want to pay attention to the date this was submitted, June 1992. What's significant about that date, of course, is that it follows Raffaele's classic paper here that was presented at a workshop on ferroelectrics in the Williamsburg series. So I think this may have been the first or second Williamsburg workshop that I went to, and I brought along my promising postdoc, Dominic King-Smith. And at that Williamsburg workshop in February '92, Raffaele presented this paper that basically had the equation that said that change of polarization could be found by integrating along a path of, you know, dp d lambda along a path. And the question that was discussed at the workshop is, does it depend upon path? And so while we were following our own path from Williamsburg back to New Brunswick, it's a 5-hour plus car trip. So we had lots of time to talk to each other. And I remember the whole time we were discussing this issue and we were thinking, yes, it must be the same, but maybe it's only the same modulo quantum, and what could that mean, and so on. So this was a very exciting time. The Williamsburg workshop was followed by other workshops, but I also want to emphasize that the subsequent developments, and by the way, our chairman, Nicola, was involved in many of these, were enormously supported by the CECAM workshops that at that time were all in Lyon, which was a wonderful place to visit also, by the way. There was this 1995 one on theory of polarization, then some on Wannier functions, anomalous Hall effect, more on maximally localized Wannier functions. All of these topics are really rather closely related in terms of their formal structure. And I'll just end by showing this lovely photo that Nicola found. So this is from the 1999 one of these CECAM workshops. And so the two speakers here and our chairman, here we are 20 years ago. And you also see Walter Cohn, who was really the father of the field and a great influence on all of us. And there's Joshua Zach. He was really, it was really interesting to have him at the workshop. Most of the people at the workshop were from our computational electronic structure community, and he was not. And so he, every time we would take something for granted, he would say, no, why do you believe that? I mean, someone made a statement about, well, we calculate the first order change of charge density with electric field. And Joshua Zach said, no, that's not well defined. And then we said, yes, it is. And he said, no, it can't be. And then there was this discussion that would go on for 45 minutes. And it was wonderfully valuable for all of us because it helped us understand what we could count on and what we couldn't count on. And when we had convinced Joshua Zach of something, we were really satisfied that it was correct. So that's all I had to present for you. And I'll have more to say probably in answer to the questions that come up later. But that's my my little initial blurb.
Thanks, David. And I have to say, having had a lift on your car, driving actually from, I think was DC, you picked me up in DC to Williamsburg, I realized that, you know, you're actually much more an Italian driver than an Anglo-Saxon driver, and I was absolutely terrified. So I find it very remarkable that actually, you know, all these ideas could be developed during such a road trip. I think Raffaele has also some recollection.
Let me share the screen.
Yes, thanks.
Before sharing the screen, I say something adding to the CECAM. Since I was the co-organizer of all of those workshops mentioned by David, I always try to have in the audience people outside our community. So sometimes we have mathematical physicists like George Kazak and others, and other times we had quantum chemists. So I tried to enlarge the CECAM. I was thinking that the CECAM workshop was the ideal place to gather also people which did not know about the theory, didn't know about the development, and to learn also something from them. Then after that, let me share the screen, because all happened in 92. David had said something. I will say something more about what happened in 92, but let's say two important things before 92. Before 92, so before I met David, of course. It is here. This is a paper which appeared in February 74 by Richard Martin. Is a comment, is a negative comment on a wrong paper. I should, let me enter the full screen maybe. And the author of this paper was not what in Italian we would call a Pellegrino. It was the author of one of the authors, probably the senior author of the reference book in lattice dynamics, and he said something really incorrect. And Richard Martin tells in this paper very, very sharply and demonstrate very simply, polarization of a crystal cannot be derived solely in terms of the charge density, a unit cell in an infinite periodic crystal. So this statement was demonstrated very clearly, and this statement still has not percolated, as I said before, to the textbooks on which our students study. So this was the way. Now, the lattice dynamic effective charge are linear response properties. So the induced macroscopic polarization was a problem which in the 70s and 80s has been mostly solved in several ways. Via linear response theory, first electric matrices, then the Baroni-Giannozzi test approach, which was extremely powerful. It was developed in the 80s. But still, one baffling part was the spontaneous. What is a spontaneous polarization? So it is measured in ferroelectrics. We have to understand what it is. First of all, we have to compute to see what it is. But in fact, this was, as Dan said, the change of paradigm. We had to define in a different way than in textbooks, and that was the starting of the theory. And now, before moving, so there is another important paper, but I have a deviation here. You know, we won a prize with that paper in 1990. The savants à l'honneur were Michel Pasternak, Alfonso Baldereschi, and me. And you may notice that there was a prize, a conspicuous prize, 20,000 Swiss francs in this prize. So before boarding my train, I went to the prize ceremony, and then before boarding my train to Trieste, I cashed the check, and my share was 6,600 francs. I went to Bucherer here, place of Saint-François, and I came with a watch for my very, very wonderful wife, you see here. And she was wearing this, even not this picture, on purpose, this picture is on my large archive from 1992. 1992 is exactly the year of the very phase.
We are not seeing the picture. We are seeing a Richard Martin's paper.
Why? On my screen, I see the. You don't see that?
No, maybe try to stop share and share again. Maybe. Oh yeah, there it is. The Seymour cry. Yeah. Now we see it.
If I go into full screen, you don't see anymore. Let me go. I had this, but into full screen mode. Do you see this? Do you see the previous slide?
We see the Seymour Cray prize. It didn't go to full screen though, but we see it very well.
Let me keep the screen. If you see the old slide in this way, you see the old slide. I guess you see.
Yeah.
Okay. Yeah. So let's remain like at this level. So I spent the money here, and this is the watch, which is in fact the Seymour Cray prize of always here. The picture was taken in 92. 92 is the year when the very phase. notice that Croatia was at war. So there were the war in Croatia, the Yugoslavian wars, but the island was very safe. The front was rather far away from the island. So we were there even with a rather costly watch. We didn't fear to be robbed. Now, what the work is about is here. This is the zone IRMA, because the IRMA is the acronym of the lab at that time. And we, for the very first time, we were able to compute spontaneous polarization. As I told you, induced polarization, linear induced polarization was something which was solved by the time, very, very accurate in several ways, but spontaneous. And then this is not yet the final idea. This is a brute force calculation, but the message we gave here, this is the journal, this is Flash, anyhow, this is Flash is the journal, I don't know whether it's called still Flash, the weekly journal of the students of EPFL. But here in Flash we wrote in French, I translate, from the phenomenological viewpoint, spontaneous polarization is not something which can be measured like as an intrinsic properties of the equilibrium state, because experimentally you only measure variation of T. That is piezoelectricity, ferroelectricity. The fundamental idea of this work is, in order to obtain the value of P, use equally the concept of difference. And our numerical experiment was actually not measuring polarization itself, was measuring a polarization difference. So this is really the change of paradigm. And after the paper in 92 was the idea that this polarization difference can be in principle computed by computing the integral of its derivative. And since the derivative was a first order, we knew how to compute the derivative. We were trying to do that, but was very difficult because under complete basis. And all of a sudden came the marvelous paper by David, very elegant and very powerful computation. And I'm glad that you say that you were not happy how the paper has been written, because I never confessed it to you before, but I had the same impression. I didn't tell you, but I said, with this result, if it's written better, should pass very fast. I had the same impression that could, given the important result, could have been written better, and I'm glad that I never dared to tell this you in order to be in some sense insulting, but instead I agree with you. So what happened is I went to the United States in February, and there was this, I presented this, they went back, I came back in the United States in May or June for the electronic structure workshop, and I checked it on the web that was in North Carolina, Raleigh, and they had a poster. And for the poster, everything became clear what had to be done. So I don't keep a journal, but I had a logbook of the boat. So I checked that I sailed only 1 month since July 7 to or July 8 to August 7. And for sure, about mid-August, I was in Lausanne working at the very phase, and we submitted our paper in October. Yeah, okay, so this is all I wanted to say at this point, and then we are ready to answer to other questions.
Thank you, Raffaele. And you know, I have some questions for you, but I would also encourage you know, the friends in the audience here to also raise their hands, ask questions. I have to confess, I've actually seen Richard Martin over there, so it would be wonderful to hear from him, because
he is online.
I think so. I mean, I remember, you know, being given the Pica, Cohen, and Martin.
In fact, it was inspiration at the beginning of my career. Yeah. Yeah.
My very first thing, and that was, you know, the, I think, moment in which either you change field completely or you dive very deeply and you understand what is written in that. But as I said, people are very welcome to raise their hands ask questions. But maybe in this theme, I will ask to both of you. Maybe we invert. I ask first to Raffaele and then to David. If you go back, what have really been, the most meaningful experiences for you in terms of learning? That is, it could be a high school teacher, it could be your university professor, it could be a paper that you have read, it could be something much later. But what do you recall as major experiences in your scientific growth?
Well, you asked several different questions in a sense, because there are different classes of answers. As for person, I know that this is my high school teacher in mathematics. So otherwise, I would not be here today, I would say, because he inspired really a passion for beautiful mathematics. He was a very old-fashioned man, did not teach me modern mathematics. What was fascinating was implied, for instance, so 2000 years mathematics, so that, or things of that kind, not really modern. Also, I was in the classical issue. He was a very old guy. He was born in 1899. He was the first war as ragazzi del 99, something about that. And so he was old-fashioned in style. He was on touring, which is also old-fashioned, but was really great. And all I learned about how to pose myself in front of mathematics, not physics at the time, I owe to him. Yeah. Then instead, if you say the professional career or the moment or the like, is when I arrived in Lausanne. So as I said, along the 70s, I wrote some papers, some of them also partly important, but part of the time, thanks to the tenured position, I was semi-professional sailing. For all of the 70s, my CV, as I said, was for sure more impressive than my CV as a physicist until the end of the 70s. And then in November 79, I arrived in Lausanne. I arrived in a building of studio apartments. In the same building, there was Stefano Baroni, just arrived as me in another studio, and Roberto Carr was already living there. But what is important, modern computational physics was born exactly in those years, I would say in Berkeley by the end of the 70s, early 80s. And we were immediately just in the middle, and this is thanks to Alfonso Baldereschi. So we were immediately in the middle of this kind of modern physics. Very few labs in the world. By now, there are thousands of people working in so-called total energy methods for solids, but instead, by that time, the majority condensed matter physics was of a different kind. So let's say Schrödinger equation for real materials, I would say something which started exactly those years. And I was first in Lausanne and then in Trieste. I was really in the middle of the action up to the culmination of that with Carparinello doing the very first simulation on the terminal nearby ours, I would say in real time. So that's the moment when I got immersed into the modern theory of materials. Yes.
Thanks, Raffaele. And if we cross the ocean, how was it for you, David?
Again, it's a little bit of a difficult question to answer because it's so open. I certainly had teachers, especially in college, who very much deepened my interest in physics, mathematics and physics. My thesis advisor, John Joannopoulos, was an enormous influence, as was the other advisors, Stephen Louis and Marvin Cohen, that I worked with as postdocs, that really got me interested in the field. I think as I moved along in my research career, there were people that I didn't know personally so much at that stage, but I really respected their work. Actually, Richard Martin, I'll mention right away, is one of them. Walter Cohn, of course, is another one. They wrote really fundamental papers. Another another influence I'll mention, this is a name that you don't hear very often in this community, is Bert Halperin. So I was at Harvard for some years and had an office, a couple of offices away from Bert, and he was working on, different kinds of things. But the thing I learned from him, he was passionate about getting to the bottom of anything. I mean, you'd have a discussion at the blackboard, and he did not want the discussion to end until he understood the important fundamental point at the bottom of the discussion. And so discussions would sometimes go on for quite a long time that way. So I learned that tenaciousness, I think, to get to the bottom of things from him. And then I learned a tremendous amount, and this goes to Nicola, from all of the students and postdocs who worked with me over the years, because I think all of us appreciate this over time. The discussions that you have, the ideas flow both ways, and it's really been a wonderful part of the reward of the whole career is interacting with young people and having them develop and then go out into the world and do wonderful things. And so, but also having learned from them during the time that they were with us. So that's my answer as best I can give it.
Thanks, David. And I relate an experience I had, I think 1 or 2 years ago, a student, I think, of mine, told me, this is a calculation with 300 atoms, and it's very expensive, and it takes 3 hours, to accomplish. So I was shocked. I thought it would take, several days on a supercomputer. So can you tell us a little bit how was it to do actually quantum mechanical calculations, sort of in the days when you sort of were, developing the theory of polarization, or even earlier? And I'll ask to David and then to Raffaele.
So I'm trying to, I mean, certainly I started out in graduate school carrying boxes of cards to the mainframe computer, and you feed them in. And, in those days, you had to be very careful to write your program without bugs because it would take...
I'm sure people would know what is actually, when you say a box of cards. I mean,
yeah, I know. Yeah. We should... sometime we should do a demonstration or something like that. But so I don't know what in the 1990s we're talking about. So we did have our own local computers at that time, but certainly, how should I put it? The even a relatively small computer is enough to challenge you to figure out what is the correct way to calculate something, because you can calculate it first on a small unit cell system. And so, the fundamental issue of figuring out the theory of polarization, didn't require large computers. Requires a large computer to apply it to a particular system that has a large unit cell. So I think, in my career, I've never really been attracted to the cutting edge problems that require really large computing. I'm more attracted to the interface between the algorithms and the physics, where you can do toy model calculations, sometimes with tight binding models and not even ab initio. So for me, the total computer power has tended not to be such an issue. But I think it was Jim Chalkowski who said, is it Jim, who said that even though the increases in computer power that have occurred over the last decades have been enormous, even more important has been our advancement in understanding of the correct way to formulate the physics of materials in terms of our ability to compute things. So.
Yeah, I remember him exactly stating, if I had to choose between the computers of today and the theories of 30 years ago, or vice versa, yeah, I would choose the theories of today. And Raffaele, how was it for you?
Yeah, of course, we were carrying boxes of cards, even in Lausanne, not in the same building, so you had to walk with your heavy boxes of cards, and then come back the day after to get the output. So you leave the box, the batch of and then the computer crunches, and then you come back. And there was no graphic, of course. The graphic was with the, I don't know, with Trasferelli, so you could attach. In the university, I worked a little bit at Purdue. There was a professional drawer, so I gave a sketch to a professional and a drawing made by a professional. But instead, we had to prepare. We had to prepare the drawings by ourselves with those letters which you stick off, and also the lines and the light. So there was no graphics. The graphic came in with PostScript. When I was in Lausanne, the second time I was at Lausanne for a long period, toward the end of the 80s, and I learned to code in PostScript. So even by now, all of the pictures by me you see, if they are not taken from somebody else's work, if they are done by me, they are done just coding directly in PostScript. So I had the PostScript code written by me. So this is, and for electronic structure, the first principle code were I would say, were done at home. They were domacio, I would say, in Trieste. No, they were a domacio thing. That is, everybody has his own version. So we had one in Lausanne, which was not really first principle. When we came back to Trieste, there was Stefano has his own and Roberto has his own. And then a student from me, Abdalaktesh, wrote one from scratch. So there was not the standard code people would use, as instead was already common in quantum chemistry. But in our domain, the code which can be used by the person who has not developed did not exist in the early 80s. We had our one. Yeah.
Yeah, I'd like to just, I think that's a real paradigm change in terms of how our community behaves that occurred. I think it was still in the 1990s. It was still the case that, most groups, my group at Rutgers, different groups at different places, everybody had their own first principles code that they had, taken probably from when they were a postdoc or something, and then modified it on their own and so on. And that's very valuable for learning what's really in the code. It's very useful from that point of view. But of course, it's not practical when you start to compete against a code like Abinit or Quantum Espresso that has so many features. I mean, our Rutgers code couldn't do metals, for example. And so that didn't bother me at the time, but so that's a real change in our community, that now we use these community codes, and maybe there's another paradigm change coming, that we rely on the big groups like the EPFL group to do all the calculations for us, and we just go to databases to get the answers. But hopefully we're not going all the way in that direction.
Thanks, David. And I think
as I already said in my talk, in the recent years, we do computational physics on the laptop, not on the supercomputer, and all of them typically by type binding or similar things. And then you can discover new theorems, new features, just something you do not expect. There's several computer experiments, despite the very simplicity of the model, you don't know the answer beforehand. And sometimes the felicitous times, what you get is a surprise. You understand something which you had not understood before, even with the type binding.
And if I can just interject, the perfect example of this is a paper that Raffaele and I and our postdocs wrote together. The first paper about orbital magnetization was wrong. And we had what we called the local circulation part. So we had the Wannier function, and we computed the circulation in the Wannier function. We said this should be the orbital magnetization. And we wrote this paper. And the two postdocs were Timo Tonhauser and Davide Cerasoli were trying to do type binding calculations to confirm that what Raffaele and I were convinced had to be right, and they kept coming back and saying it doesn't match. And we'd say there must be a bug, and they'd come back and say, no, it doesn't match. And eventually they convinced us. So that was a wonderful experience.
Thanks, David. And I was saying, in the best shows, we have actually a mystery guest that has appeared. I'm really happy to see Richard Martin. I suppose from Palo Alto, Richard. Where are you joining us from?
You have to unmute.
Oh, okay. Can you hear me?
Yeah.
Yes, Palo Alto. It's really nice to be here, and I really didn't want to miss those nice talks by David and Raffaele.
So very, very much welcome. And so we dragged you in because I think besides, being very honored to have you here, I think it would be great to hear also your perspective of, what have been, the educators, the scientists, the works that have really put you in this field of electronic structure theory and calculation. What has really influenced you in the early stages?
Oh, wow. Well, let me say first that I really appreciate the nice comments by Raffaele with my paper, and by David too, of course. I was really proud of that, and it was a time when it was kind of fighting against some other people. So it was, it was nice, and. So I had zero idea about the pretty things with Berry phases and all that, but we gotten to the point where it was clear that there was a current that flowed through the unit cell that had to be taken into account. And by the 1980s, we had some computers and actually were doing some calculations on materials, and we actually tried to calculate the current, the hard way. And so it was really nice for Raffaele's expressions for the current, and David and Kingsmith's paper that showed that you got an answer independent of the path that you chose. And it is pretty Berry phase stuff. So I had zero idea about that beforehand, and you really put it together. So back in the day, then you can just imagine what the computer calculations were like in 1974. And so I had done calculations on with the lattice dynamics, with 8x8 matrices, and on the computer with overnight calculations. But the thing that relates to what David Vanderbilt was saying was that the person who mentored me most of all was Morrow Cohen, and then also Walter Cohn. So the two were just, they're just really great people, to say the least. And it was Morrow Cohen that pushed me to sort of always look at things from the deepest point of view that I could. That just follow them through. Don't give up and think that something is right just because you might be close to the answer or your desired answer or something like that. But to look why. And so that was the business of the polarization.
Richard, didn't you tell me once that Conyers Herring was an influence on you also?
Oh, yes. That was a little later, actually. But I mean, I should have had this influence from him when I was at Bell Labs, just a little earlier. But somehow I was blind enough not to get the best influence I could have had from him. But you're 100% right on Conyers, and he was even more so in terms of following through and really looking for the answers down deep. I have a little story about the polarization that if you wouldn't
please
mind me telling. This was with Mary Duden on that related to that paper that Raffaele showed, and he was not all that happy about saying he was wrong, just basically deeply wrong. And I visited him in Irvine, where he was at the time, and you might know that he is of Russian descent or something. I'm not quite sure how Russian he was, but definitely it was at least in his family descent. And I was at the board in his office to explain to him why I thought his calculations were wrong. And then suddenly, boom, right beside me on the blackboard was this shoe that he had thrown across the room and hit the blackboard. And this was even more amusing because it was just after the time when Khrushchev threw his shoe at someone in the United Nations. So it really added to the little story that I have about that period of time. So, okay.
Richard. Thanks a lot. I have a question coming through the chat that says, thank you for the great talks. Though developing new theories takes time, and unfortunately the pace, pressure, and rush of research nowadays makes it difficult to dedicate time to fundamental problems. What could you advise to younger researchers on this matter? And maybe we'll get David, Raffaele, and I'll ask Richard as well, if you feel ready to give advice to the junior scientist that, in 30 years, they'll say, I followed that advice, or I didn't follow that advice, and that was very important.
Yeah, it's true. It's very hard to keep up with things nowadays. It was much easier in earlier in my career to, I would leaf through every issue of physical review letters, the paper copy. I would leaf through to look for interesting papers, and been a very long time. And then there was a while when I used to kind of try to catch all of, browse through all of the archive cond mat titles, and I don't even do that anymore, so. But I guess my answer would be just you should set aside some time. You find some way, maybe, Friday afternoons or whatever works for you, set aside a time where you put all that other stuff away and pull out the projects that you're interested in working on, and, turn off the phone and and spend some concentrated time. That would be my recommendation.
Thanks, David. And Raffaele, what would you
say? By now, computational physics is done by very, very large groups, so like yours, for instance, and many others in the world. And so it's clear that the young people, in some sense, have a short, a near aim, that is they don't have time. My kind of physics by now, so particularly something, I have at most one student, and I try to figure out new things. And instead, if young people has to start a career in computational physics, I would not recommend to try to have a career in this style, that is style banding and the like, unless you go into topological insulator, something very, very, very fashionable or the like. And so instead, the few students that I had, all of them after entered into ab initio, first principle, and quantum espresso calculation, typically, or things like that, I would say.
Thanks, Raffaele. And Richard, we'll ask you also the question. So what kind of advice would you give to new researchers in the field? If any, of course, but...
Oh, okay. Wow. Well, the main thing would be to look deeply at any problem that you're working on, and with regard to keeping up the literature. Wow. Somehow I can imagine that if I were way younger, I might be able to figure out ways to sort through the literature and pull out the things that are most interesting, since there are all these ways to sort things. So 20 years ago, I was so proud to make a list of other electronic structure groups and things like that, and where are their websites, and try to make this available online that other people could find. And then that's just useless now. You can get that way quicker just by typing in a name or two, and anything online. So it would be I have the hopes that we'll be able to come back to more easy ways to find things in your own field, things that you sort of already know about, and then pay more attention to the things like David just said, you know, really trying to look for new things. And hope you see what I mean, and not just get overwhelmed by this huge amount of data, but organize it in good ways and still be looking for new stuff. And using computers in good ways, like using the databases, which I just don't do at all, but can imagine that there could be, you know, really good ways to use these things. So.
Thanks, Richard. I can't resist actually offering my own advice because, you know, hearing actually David mention, you know, the work that he and Raffaele and Timo and David did, you know, I realized and I learned that actually, you know, when things don't work is actually the time when you learn something, and you should really be happy when something doesn't work and something doesn't make sense, because, you know, this is the time when you make progress. I think we are getting close to the end, I think. Also, I don't want to keep everyone beyond what is 6 here. So I have a mystery question for our two speakers, for David and Raffaele. And that comes from the BBC. I don't know how much of you are familiar with the Desert Island books, but basically there is the question, you have to be stranded on a desert island. And so the only thing that you can do is bring with you one book, one piece of music, and one luxury item. And so the question for David and Raffaele is what book, what music, and what luxury item will you bring? And I don't know who of the two of you is ready first to answer this question.
Well,
yeah, I'll let Raffaele go.
Yeah, I'm ready because the broadcast exists in Italy every Sunday morning, and also the lady the host of this radio talk has a PhD in mathematics, so is Chiara Valerio, and so I made the exercise in advance. Suppose she invites me, what I would like to tell, and for the book, no doubt, I have the Histoire de ma vie of the great Giacomo Casanova, for sure. Of course, in the French edition, La Pléiade. But at the second place, I would put Orlando Furioso, Ariosto. And for the music, if opera is allowed, is La Traviata, of course. And then the movie is more difficult. Many movies, historical, dramatic. So let's say Fellini, Vitelloni, for instance, something like that.
Thanks. I love them. Very Italian, I think. So I'll pass the question to David then. David, what would you?
I'm unprepared for this, so I'll give frivolous answers, I guess. For the book, maybe War and Peace, since it's really long, and then I don't have to reread it so frequently. And
as a novel, is 3,000 pages, including notes.
And then what the second one is music. I don't know. Some jazz anthology or something like that. And the third one is what?
Well, it was a luxury item. Actually.
Luxury item.
Yeah, it became a movie, but you can choose.
Well, I don't know. I guess I have this watch, and I love this watch. I actually got an Apple Watch a few years ago, and then I stopped wearing it after a while, and I went back to this watch. I don't know if you call this a luxury item. It's not, but it's, you know, it's actually mechanical, electromechanical. There's some semiconductor electronics in there. It's got a little photovoltaic sensor so that it never has to be wound or shaken or anything like that, and it just goes forever, and I love it. So I would want to have that with me on the island. It's a reminder of what technology can do.
Thank you, David. We are live from Switzerland, of course, so I can't see any better sort of fitting conclusion. So,
I'm sorry, it's a Japanese watch, but anyway.
So with this, I really want to thank David and Raffaele both for the beautiful talks and for being game in sort of this live session at the end. Thanks, Richard, for graciously being our mystery guest.
Thank you for letting me be there.
Thanks for
I
joining.
think Beverly passing behind, so
That's correct.
issues to Beverly as well.
And she wasn't here to see Bettina's picture, which was wonderful to see.
And of course, Ignacio and Sarah from CECAM and Patrick that coordinates all of this. Nothing of this will be lost. It will be recorded and available together with all the databases on the CECAM and the MARVEL website. So with this, I thank you again, all of you and all our audience sort of near and far.